Hello, and welcome to the first lecture in Module 1. In this lesson, we're going to distinguish between hazards and risks, survey the range of hazards in a workplace, recognize that many behaviors and unidentified hazards contribute to incidents and accidents, and classify risk control measures according to the hierarchy of controls. Researchers should identify hazards and assess risks to reduce the likelihood of harm. A hazard is a condition or a set of circumstances that can cause harm. In other words, this is potential for damage or harm. A risk is the likelihood that a hazard will actually cause harm and the severity of that harm. And a harm is an actual physical injury or damage to health. So let's look over a few examples and see if we can properly identify them as a hazard or a harm. I'm going to give you a few seconds to think about these before we go over the answers. So in the first example, Mycobacterium tuberculosis, this is a hazard. This is a bacteria that can result in tuberculosis. Number 2 is laceration. This is a harm. Sharps have the risk of laceration. Number 3, welding is a hazard. It can cause damage to vision, or it can cause burns or toxic exposure. Number 4 is electrocution. This is a harm. Electricity has the risk of electrocution. And number 5, metal fume fever is a harm. Welding has the risk of metal fume fever. Hazards come in various forms. Here are a few examples. There are environmental and physical hazards, including noise, heights, temperature, enclosed space, electricity, equipment, sharps, and pressurized containers, and chemical hazards, including chemical toxicity and chemical energy, and biological hazards, viruses, bacteria, and fungi. We've reached another self-check. What category of hazard does a lathe pose? In 2011, an undergraduate student just weeks away from graduating from Yale was hard at work in the chemistry lab. She was exploring the use of liquid helium for detecting dark matter particles. While using the lathe, her hair became entangled in the rotating axis. Her neck was compressed and she asphyxiated. Sadly, she did not survive the harm caused by the equipment. The hazard was the kinetic energy from the lathe. This is a physical hazard similar to the risk of a centrifuge. The risk of entanglement can cause a variety of harm, including scalping, limb mangling, dismemberment, or asphyxiation. Risk considers likelihood of harm and severity of harm. The likelihood of harm is categorized from rare to certain, as you can see in the table, and the severity of harm is categorized from negligible to catastrophic. For example, irritation would be negligible or marginal, while cancer would be critical or catastrophic. The severity of harm can be influenced by the nature of exposure, whether it's chronic or acute exposure, and the exposure route. The exposure routes are inhalation, skin contact, skin absorption, ingestion, and injection. We'll talk about those more when discussing personal protective equipment in a later module. Risk can be stated either objectively or subjectively, qualitatively or quantitatively, in general terms or in mathematical terms. A mathematical term might be something like an LD50, which is a lethal dose 50. We can also talk about that in a later module. Accidents and incidents are not synonyms, and definitions may vary. In the first schematic, accidents and near misses are both viewed as a type of incident, where the second scenario views accidents and incidents as two kinds of events. At Embry-Riddle, we use the second definition, where incidents can refer to a near miss, which is an event where someone almost got hurt, or an undesired circumstance, which are circumstances that could lead to harm. Let's go through a scenario to explain these terms as Embry-Riddle applies them. Imagine you're in a chemistry lab and a spill of a toxic chemical occurs. This is an undesired circumstance. If someone then steps in the puddle and slips, but doesn't fall, thereby avoiding any physical injury from the fall and exposure to the chemical, that's a near miss. If the fall was not avoided and the person is either injured in the fall were exposed to the toxic chemical when landing, the incident is reclassified as an accident. For every fatality, there are 300,000 at-risk behaviors and 3,000 near misses. That means many risks are controlled. So, how does an accident actually occur? The Swiss cheese model of accident causation shows layers of barriers between decisions of the top management and accidents. Each slice of cheese is a barrier to prevent errors. Each hole represents failures in the barrier. A hole may be latent or actively opened by individuals. Let's go through a situation. At Texas Tech, Preston Brown was injured in a laboratory explosion. How did he arrive at this unsafe act? Let's start with the first slice of cheese, the culture, leadership, and policies. His project was funded by the Department of Homeland Security, which failed to stipulate safety standards in the grant program. Also at this level is the incomplete fit of safety policies that are designed for industry but applied to academic research labs. Also at this level, the university did not assess the overall dangers posed by this potentially explosive material, nickel hydrazine perchlorate, which I'll refer to as NHP. The university did not require PIs to report near misses and did not consistently establish and enforce accountability for safety conditions. Looking at the second slice of cheese, the university's safety administration did not adequately review the project to ensure proper engineering controls and infrastructure were in place. The third slice of cheese is the responsibility of the principal investigator, providing supervision and training. Preston's PI did not identify a limit on the quantity of NHP he could produce. He also did not train him specifically on the handling of NHP. The PI also did not enforce the use of personal protective equipment in the lab. Preston Brown was not wearing his lab goggles. He was also making a larger than typical batch of NHP. He noticed it was a bit chunky. Here comes the unsafe act. He placed a contact explosive in a mortar and began to grind the chunks apart with a pestle, falsely believing that wetting it with hexane would prevent detonation. He was wrong, and the resulting accident caused eye damage, severe burns, and the loss of 3 fingers. Unsafe acts are active failures. Just as an unsafe act can result in an accident or incident, unidentified hazards are not properly controlled and thus carry significant risks. A thorough risk assessment can ensure all risks are identified, evaluated, and controlled. Risk assessment is the process of identifying hazards, evaluating risks, and determining appropriate control measures. The first step is to identify the hazards. This can be done by collecting existing information and by performing inspections. Once the risks are identified, they must be evaluated, which may require fact-finding. Ask yourself, how likely is it that this hazard will cause harm? If it can cause harm, how often is the risk of harm? And finally, if harm does occur, how bad will it be? It could be minor, bruising, cuts, light abrasions. Serious harm is often reversible and includes loss of consciousness or burns. A major harm is normally irreversible, including loss of sight, permanent disability, respiratory damage, or limb amputation. Obviously, the worst case scenario is that the harm is fatal. Risk is managed using a hierarchy of controls. The most effective option is to just eliminate the risk altogether by removing the hazard. Why use a toxic chemical when a non-toxic chemical can achieve the same result? Why perform an operation at heights when the object being repaired can be removed and repaired at ground level? Unfortunately, elimination is ideal but not always practical. Substitution is the next best option. If you cannot remove the risk, is it possible to use something less risky? For example, can you use toluene as a solvent instead of benzene? If the hazard still exists after considering elimination and substitution, you can isolate the hazard from the worker using engineering controls like machine guards, noise dampening technology, fume hoods, and remote operation. Less effective but still valuable are administrative controls. Administrative controls include training and procedures like standard operating procedures, training schedules, permit to work programs, warning alarms, and labeling systems. The very last line of defense from harm is personal protective equipment, PPE. This equipment is placed directly on the worker's body, including respirators, gloves, hats, goggles, and earplugs. This is the least effective method for protecting workers from a hazard. The hazard is still present. Equipment can fail. No PPE is foolproof. PPE isn't comfortable to wear for long periods of time and can itself create hazards. Long-term respirator use is hard on lungs. Tyvek bodysuits can increase body temperature. Gloves can reduce dexterity. We've picked up a lot of new vocabulary in this lecture. You can now distinguish a hazard from a risk. We discussed how risk is categorized based on likelihood of harm and severity of harm. We discussed Embry-Riddle's definition of an incident, accident, and near miss. We've introduced the types of hazards in a workplace, including environmental and physical hazards, chemical hazards, and biological hazards. We walked through an accident at Texas Tech, applying the Swiss cheese model. Most accidents result from an unsafe act, meaning it was an active failure, a bad decision. But unidentified hazards also carry significant risks. Risk assessment identifies risks, evaluates them, and establishes control measures. The hierarchy of controls places elimination as the most effective strategy, while PPE is the last line of defense against a hazard.